So this is
Uh,
session 7. We're covering this is the third session on the JIT.
yes. So, um, let's see. Refresh my memory as to where we left off.
Um, oh, that's a real good question.
Let's see. We got through the actual JIT. We were going through the actual JITify code.
Yeah, we got to well, I really should have looked at this first. I got all distracted with the Postgres issues.
We uh,
Yes.
we looked we looked at what happens when you call the JIT and what path does it take. And we're talking about the critical sections and the JITifier load. We started that this is the key entry point for all the JIT wrappers. Okay. I think we got into this critical section, the load to the critical section part of the compiler that we're going to shell out to the compiler. Oh, and we talked about, oh, I know what we did. Oh, we talked about the pre-JITs. How do I verify the pre-JIT kernels? And then the user-defined ops and types are handled differently as well. And then we did this. It's like, oh, I didn't find the hash table. So, oh, wait, you can't compile, you can't load. So return and GRB no value. Um, I've thought about, by the way, I've thought about this. If you compile, here's a case for the JIT. Here's an example of what can happen in the JIT. Suppose you have a user-defined operator, user-defined type, and you have a typo in it. It's a compile. You left off a semicolon, something stupid, right? And it's not going to ever compile. And you stick this object in and I'm not going to know that until I try to compile. And then something went wrong in the compiler, and I don't know what. And so let's suppose you get the JIT full on run or on, the JIT's on. So you're going to compile and it fails. And you have a call to GRB MXN with a semmering that's never going to compile, and you call it 1,000 times. Do I try to call out to a compiler 1,000 times? No, that's ridiculous. That's going to take you 2 seconds each call. It's ridiculous, for a 10 by 10 matrix. So I don't do that. To get around that, what I do is I say, look, if I run across any nasty error like that I can't control, I turn off the JIT. So if it's on, I turn off the ability to compile. If I try to compile and I can't, I turn off the compiler. I ratchet down. There's 5 states of the JIT. On, which means I can load and compile and everything else. Load, which means I can't compile, but I can load and then run the JIT. Run means you can't load from disk, but if you've got a JIT kernel in your hash table in memory, already DL open, you can still call it, use it. Pause means keep it in memory, keep it JIT kernels in memory, don't reflush them, but don't call them. And then off means flush out, DL close everything. There are no JIT kernels, they go away. Okay, so what I do if I fail to compile, I ratchet down to, or you can only load. If I fail to load, I ratchet down to run. And I think with run, I never, like if it's not there, I'd say, well, sorry, it's not there. So that's my workaround to if there's a compiler error. I hide, then if it fails, I'll punt to the generic kernel, which can be very slow. And surprise, it'll work. That's good. But what if you're developing and you really want to know, oh, wait a minute, I really want this to JIT. So I really need to have, but so at least in development, you may wish to, I mean, if you just want to get the answer, okay, default is just get the answer, Tim. If it's slow, so be it. Just get the answer. Or wait a minute, the JIT failed. I want to know that. I want to return a panic because something bad happened. So this return value here, I think I need some user control over which they want me to tell them. Like, whoops, something happened. Like
Like a
I
set
wanted,
where I can
yeah,
say
a global
panic on.
set.
Yeah.
Yeah, what happens if the JIT fails in any way? Like, I don't want to go to generic. I want to go to the JIT. And if the function's not JITable, like you didn't give me the string, I'll return panic maybe, because like I can't JIT it. What do you mean? That's maybe a different level. So there could be layers. See, that's not this error. That error comes when if I can easily detect, hey, the hash is infinite. The hash is uint64, int64 max or something like that. That's a special code for the hash of this kernel that says it's not JITable by any stretch. And I know that to be the case because you didn't even give me the strings. Okay, that would be different. That would be another error that, well, there's no way I could ever JIT that because you forgot to give me the strings. Well, do you want that to panic? Maybe. But you didn't give me the strings in the first place. So what do you expect me to do? If you give me the strings and I can't JIT it, well, maybe you want to know that. So maybe there's 3 settings for the JIT return value that say, tell me what you want me to tell you if something goes wrong. And I don't know that there's a single answer to that. So maybe it's a set that says, yeah, a global setting that says, by default, it's I'll do the best I can to, and I'll call it generic kernel, or panic or something, or JIT panic. Maybe there's a different error code other than panic that could be returned. I don't know. I would probably, since I'm not, well, see, panic is in the spec. Panic is brutal in its definition. It basically says anything else you do with GraphBLAS, just go away. You can't even trust GraphBLAS to do anything for you anymore because something horrible happened that GraphBLAS cannot recover ever from. Go away. Just shut off GraphBLAS. Well, that's pretty extreme. I never return panic as a result. Panic is not just, oh, some error happened. No, it's a fatal segfault kind of level of, just shut off GraphBLAS. So panic is too extreme. I need some other flag, some other error code that says, sorry, can't JIT it, but you can keep going if you want. It's not a panic. And I think I need at least 3 levels of control, like if it fails to compile, because if you look at, say, I don't know, if you look at the JIT wrappers, let's see, I get this hash. Oh, and then I call JIT load, but see, I pass in the hash. So let me go back to the JITifier load. The JIT load, the very first thing it does, it says, I mean, it's not even defined. It's unhashable. It's unhashable. This is a special code that says there's no way I would ever be able to JIT this. So it's undefined. So this would be a different scenario than the rest of the no values. Should be still a no value because if the JIT's off or paused, well, it's supposed to return no value. That's what you've told me to do. But if you're trying to run the JIT, well, then, these, it's like I tried, I'm running and I expect to use the JIT. Well, what do you want me to do there? All these different decision points. I just say no value, and then no value. Use that error code does not go back to the end user. That error code is my own indicator that says the JIT couldn't do it. Oh, then punt to generic. That's what no value means. But maybe there should be a JIT panic of some kind, or a JIT fail or something. GRB JIT fail, GXB JIT fail or something. I don't know what that error code should be.
It would be a GRB info value.
Yeah, a GRB info. And I have some of those extended GRB info.
Yeah, there's like exhausted, right? And
I think I just have one.
Exhausted, yeah.
Exhausted, yeah. I needed that because I needed to tell the iterator, it's not an error, the iterator just is done. Yeah.
Right.
So I don't have any other GXB enums for info. I haven't needed them. And I kind of don't want to, panic is too extreme. out of memory, invalid object, and empty object. See, these are two. I can't return these. These are not good either. So I kind of need, and I internally has no value, but I don't pass that back to the user. So that doesn't matter what that could be negative 999 for all I care. It doesn't matter what I use there. But I think I would need to have some. I could return exhausted. I have it already. Like the JIT's exhausted. I don't know. JIT. Oh, not enough coffee, right? If you drink too much coffee, you get exhausted because you've had too much. You're too jittery. Too much
For
coffee.
sure. Too jittery.
Yeah. So I've had this issue, say with students I'm working with. They're trying to write some code that has some user-defined operators. And in fact, I just had this with this intern who was here this summer, and she was encountering a seg fault in GraphBLAS, an actual seg fault. It's like inside GraphBLAS. That was my bug. Actually, I found it. It was a pretty nasty bug. But the reason she hit that bug, though, is because she had a typo in her operator that would thus not compile. So I was turning off the JIT when she didn't expect it to turn off. And then I had a bug in the generic kernel for an index unary op when the input matrix is ISO valued. So you have a generic index unary op that can't be compiled. So it comes to the generic method, and I didn't handle the ISO case properly, which of course was my bug. That should have always been like if she has the JIT off, regardless of the compiler error, then. But it was a weird error then for her to handle because she was seeing a bug somewhere else, not where because the thing where she had the bug, her bug, was just not defining the operator correctly, but I was masking that because oh, no problem. I have a generic kernel for you. That actually worked. It was somewhere else that failed because it needed the JIT to work.
Yeah.
It's like, what? So there are two errors coming together. Her error, which was minor, no big deal, was masking turning off the JIT, and then I would fail somewhere else. So she had a very hard bug to track down anyway. But you get unexpected performance. So I need some kind of mechanism for that. I fixed the bug, and I've just recently released a GraphBLAS 9.3.0 to fix that bug. So that's done. That's bug number 55, I think it was. That is now fixed. So yes, I need some kind of way of indicating to the caller that I tried, but I couldn't JIT it. Oh darn, the JIT was exhausted, even though I should have been able to do it. How do I? Now this is different. Like if you've told me I can't load and compile, and I come and find the kernel's not there, well, you've told me not to load or compile, so I should just punt to generic there. I shouldn't. That's not an error because something bad happened. You told me not to, so I won't, and I'll use generic. So I mean, I don't know. I've got to go through and think about where it's the API for the JIT itself. I mean, it's supposed to just be totally transparent. You just call GraphBLAS and it works. All the JIT just works, and that's what it does. But there are some settings like this that are important to consider to tweak the behavior of the JIT. And some of those they're already have those, like all those strings, right? I have, if you go to config in CMake time, I know what compiler you used. In this case, I'm on my laptop, and my laptop C compiler is GCC 12.0 through SPAC. So this got stuck. This big, huge thing got dumped into my in my config file. This big, wild-looking named compiler. And the same is true for the C flags. All these things these are the CMake things that these are the settings by default come from CMake. But if you're cross-compiling or something, then you don't want these. So what you can do later is you can use GRSB set to override these. You can tell me where the compiler is. You can tell me, you can redo all these strings after GRB init comes into play. And eventually you'll be able to do that for CUDA as well. You could tell me where the CUDA compiler is or what are the CUDA flags. You'll be able to do that. I don't use those yet, so I haven't put those strings in here yet. And besides, this is a machine on my laptop without a GPU, so those are empty anyway. Okay, so I do need some kind of revision to the JIT to handle this, and I've not yet thought about how to, or I've thought about it, but I've not yet really fleshed out how to do that. Here's another place where something bad happened. I couldn't lock the file. Why? I have no idea. So I turn off the JIT, because otherwise you'll just keep having more failures. I don't know. Is that a good idea? Maybe you want to panic at that point. JIT panic.
Yeah.
It's hard for me to know. Okay, so we're already now inside. Yeah, we're inside the critical section. This load to worker here is inside the critical section. So if you have multiple threads within one process, only one gets to JIT at a time. The locking ensures that two entirely different user processes can JIT independently if they like, but if they try to JIT the same kernel, I use the file locking mechanism to avoid that.
And one will JIT and one will wait until it's done and then load the.
No. One says, oops, I couldn't lock. I'm not going to try again.
Oh, it just goes to generic.
It goes to run and from, yeah, it turns off the JIT.
Oh, I see.
That's kind of, that's something I'd see there. That's a fix me.
I see, yeah.
I would probably want to do something different here. Sleep, maybe. I mean, I don't know. Do you want to wait a second to try again? I don't have that mechanism yet.
In Postgres, and this is just one way they handle a similar situation is you can lock and it will wait by default for a lock to free, or you can say no wait and it will fail immediately.
Yeah, yeah.
And it's basically a user option where
right. And so I have this I use file locking in just two places. I lock the whole thing, and then I lock the source code when I'm about to. Oh, wait, this is unlocking. Oh, this is when GRB init comes along, and I'm uncompressing all the source code. So I basically have two places where I lock. I have a lock file to lock that whole kernel, that specific kernel, and it's named by the hash code. So you're not going to hash to the same. If there's a hash collision, it's the same lock file. But typically that wouldn't happen. So hash collisions should be pretty rare because it's a 64-bit hash code and it's a very good hash function. It's XX hash. So it's highly unlikely that two different JITs will JIT to the same hash code. But however, it's quite likely that two different processes will want to do the very same thing because maybe they're related processes. And they both want to JIT that kernel. Well, one will get in and one will say, whoops, and it'll fail. Now, yes, I could put some kind of waiting mechanism inside the lock itself. So I have a GB file mechanism here. I have the GB file has all these functions, which are things like open and lock a file. Okay, how do I do that? Well, I try to open the file, I try to get the file pointer, and then I try to lock the file. And if I fail, I repeat. Well, file lock, of course, if you're Windows, you do _lock file, of course, because why not put an underscore before a function is called by the user? Really? Whatever. Or POSIX lock. Okay. So I have to, I mean, there is no wait thing mechanism there. I don't know. Maybe there's a different wait mechanism for waiting on Windows lock for a file. I have no idea. POSIX, I don't know. I call it a write lock. So yeah, because it's gonna write not to this file. It's a lock file that's not written to. It's just a stub only used for locking. The actual source files and the libraries and the .sos and compiled such, that's separate. This is just the file that only used to lock it. Yeah, I mean this file lock right here could say, oh, you didn't get it. Oh, let's try again 1 second later or something. I don't know. I don't know. I I haven't really figured out a good solution to this. Because it's not really been a critical bottleneck in the use of GraphBLAS anyway. I mean, what I do now is safe, just kind of overkill. Okay, so now finally I'm going to actually create and I call another function here. I probably could put the code in there because I think I mentioned this before, but I put this in a separate function. It's only called right here, and the function's right here. I put it in a separate function so I could see the lock and unlock as a bracket. Lock it, unlock it, done. And you can see it on a same place. So that's why it's in a separate function. So now finally, this code is in both inside a critical section for the process and within that file lock unlock for other processes. So nobody is going to do this same kernel anywhere except right now. So now I'm safe from synchronization. I'm synchronized against guarding its access by anybody, a thread within my own process or another process, a thread in another process. Okay, so finally, I forget, I think, let's see, did I get to this? So I think I'm to the point, I think we didn't get to this piece yet, did we? Last time? I think I'm pretty much to where we when he needed to start off from. I think I talked about the locking, unlocking, and I think we stopped there.
Yep. Yeah.
Yeah. Okay. So now it's time to load the thing, actually load it from disk, or compile it if I can't load it. So I get me the name of the .so file, and I try to DL open it. And what happens if I couldn't? Okay, so what is this file name? How is it constructed anyway? I'm just sprinting into a sprintf into a temporary string that I use for all my file names and commands and such. But this string here is the JIT cache path. That's by default tilde.suitesparse /grb 930, whatever. Okay. On Windows, it defaults to something else. And you can change it as well with grb set. You can tell me where the cache is. If you don't like .suitesparse, you can tell me to use someplace else. So that's where that comes from. And then I break that bucket. I break the hash. I break the library. This folder could otherwise get really big. It's when I run the test coverage, it's 22,000 now JITs. And when I do test coverage, so I break it up into 256. The bucket is an 8-bit number, and then I have the kernel. So it's the prefix, which is not reconfigurable because that's like for Windows, it's nothing. For Unix and Mac, it's lib, like lib graphblas.so. This is the lib in the name, and then this is the kernel name that I'm expecting to compile, which is going to have the whole, what's it going to look like? it's going to have the kernel name all the way to here. So that's the kernel name. It's the full name of the kernel with the prefix gbjit. That's always there. The name of the kernel, which could include the word CUDA if it's a CUDA kernel, and then underscore underscore is my spacing. Yeah, and then because then so I can always parse these names. I do this for the C codes as well, and then this is the encoding, not the hash, but the encoding. Okay, so that's the kernel name, and I try to open it. And if I get it, yay, I'm happy. I do the DL open, and I get it. I get a handle. So what does this mean? If it works, it's not null, but I don't know if it's any good. I may have loaded a stale kernel. So I query that kernel. Hey, DL, hey, library I just loaded. I'm querying you. I call the query function now, and I check. I get the DL sim. I have this I have the DL, the handle to the library I just loaded, and there's two symbols in it, JIT query and JIT kernel. I get the symbol for the JIT query, and if I find it, I ask, are you okay? Are you like the one I think I should be getting? And if it didn't have, if that failed, or if it couldn't find the JIT query function, which is unusual, or if it says, hey, you're different, well then I delete that entire file. It gets blasted right there with remove. And fortunately, that works on Windows. It's really strange. You can remove a file on Windows or Linux the same way. Just remove. Why not? How hard can it be? Okay.
And then the next
So,
time around, when you do the operation again, it will go through the whole JIT flow.
right, it's doing it right now. I'll show you. Because see, I close it, I remove the file,
Oh,
I
I
set
see.
DL
Yeah.
handle to null, right, which is going to trigger this condition. You see, this thing tries to load it. If it's not there, I need to compile it, and DL handle is null. If it's not null up here, oh, are you okay? Oh, you know you're not. Well, close the thing, set the handle to null, remove the file, and now it's as if it didn't even DL open. So it was stale. I threw it away. DL handle now is null, and null means I have to compile it unless I'm not permitted to. So I'm starting to get to the compiler now. Now I tried to load it, I couldn't, or I loaded it and it was stale and I threw it away. So now I need to compile it. If the JIT control is not the very highest setting, on, right? It's on, load, run, pause, off. On says you can go and compile. Well, if I can't compile, sorry, I'm not going to compile it. And you'll get generic instead. So now it's at this point that I need to construct the source code. So this is the file name of the source code that I'm constructing right here. It's in the C folder, but it will also include CUDA files because the file type is defined here. There's the CUDA specialization right there, right? I know with the kernel code, like there's 44 GB, like GB dot kernel or GB assign kernel or something. There's about 44 OpenMP kernels, and they're all numbered between the space of 0 and 1000, less than 1000. And GBJIT CUDA kernel is 1000. All the CUDA kernels have a kernel code of 1001 to 1002 and so forth on up. So I have that integer space that say, well, what are you? Oh, you're a CUDA kernel. Okay. And so same file IO and everything here. So now I let's see. I don't think I walked through this, did I? Did I walk through this? The macro
Not yet, no.
file. Okay. Uh, I think I walked through this really briefly when we were looking at the macrofy, but not in context of constructing the whole JIT. So, but yeah, let me walk through this. So, got 85 kernels here, so that's not so super crazy. Okay, so the first thing I need to do is let's see. Let me run the Gauss demos. So I'll compile those. So I think I'll run the demo. So some of these will, the first thing I do is compile the preface to the, now I'm writing out all these, like you call them X macros. These are the macros that are defining the operators, the data types, the sparsity format of the matrix and such. So that's macrofy. Now I'm having to macrofy. I think this is the first time I had to macrofy. Well, I macrofied the name to get the kernel name. I probably should. This is really the macrofy. This macrofy is different because it's writing to a string. The other macrofies are writing to files. File IO. I should probably name that macrofy name a little bit differently. So the first thing I do is macrofy the preface. I mean, okay, I just compiled all these. They weren't there before. So let's suppose I'm, oh, I don't know. Let's do apply. Why not? Okay, so here's a kernel here's a kernel that I just compiled just now. And the first thing it did was compile the preface, which is all these comments, which are kind of handy. Okay, to here. It only did this right here. This thing, it's like, wait, how does GraphBLAS know about gaussdemo.c? And how does it know to include math.h? Well, I don't actually need to include math.h. I have it already, but this is just an example. The user may have an operator that needs its own pound include that GraphBLAS doesn't know about. So you can set the preface of a JIT kernel. Actually, then it goes to all JIT kernels. There may be, so I haven't really had to use this very much, but you can tell me, hey, to compile my JIT kernel, I need this pound include. And so that's what I put in a comment just for grins in the Gauss demo main program, the demo program. I said, here's my preface. Whenever I compile a JIT kernel, I need to say / kernel by Gauss demo.c pound include math.h. That was my C preface. You will also be able to tell a CUDA kernel its preface, which I have a distinction between the two because they're going to be different. And and I pass in the kernel name so I can print the thing. There's the kernel name right there, .c. That's the full, is it the full name of the kernel? Let's see. Yeah, that's the full name of the kernel is gbjit blah 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 .c. No, .c is not part of the kernel name. Sorry, the kernel name is written out right here, and then the .c was because I know it's a C file from the kernel code. So I pass in the kernel code. The kernel code also tells me which preface to write. So I wrote the the OpenMP CPU preface, not the CUDA preface. Okay, now I'm going to do the top level macrofy, and that's going to produce everything all the way from here, both for CPU, OpenMP kernels, and CUDA kernels. It's going to produce all this stuff all the way down to right here, this line. Okay, so that's the job of the macrofy family. So macrofy family then is going to macrofy any JIT, OpenMP, CUDA, either one. And it's going to be here in the JITifier subfolder. So macrofy family, and that's it. It's just a switch case to say, Well, here's the file we're going to write to. We're going to do the entire, we're going to do a particular family. This family, though, is only used in the switch, if I recall. Yeah, it's just used in the switch. Just which macrofile do you want to call it? Are you macrofying an apply kernel, an assign, a build, EYs, like EYs multiply, EYs add has the same, it's in the same family, so they share everything. Matrix multiply, reduce to scalar, select, user op, user type. That's it. That's all the JITs I have. They all fit in one of these families. And they all have slightly different requirements, like MXM needs the enumerification code, encoding. It needs a summary in 3 types of the 3 matrices. 3 types of the 3 matrices. These are not the types within the summary. They can differ because there can be typecasting. MXM has 6 possible different types. The C matrix, the A matrix, and the B matrix. That's type 1, type 2, type 3. And it also has up to 3 types for the summary. I call them X, Y, and Z. The X input to the multiply operator, the Y input to the multiply operator, and the Z output of the multiplier, which is also the Z type of the type of the monoid. So there's 6 possible different types. And then this specifies all those 6 because there's 3 inside the summary and then 3 here. And they could all be different. So let's suppose we're macrofying. Well, let's just use this one as an example. What are we macrofying? This is an apply. We're doing a macrofy apply. So macrofy apply, I guess, has two types. I guess there's an input matrix and an output matrix. Yeah, that's it. And we're going to macrofy those types if we need to. We're going to have an operator. And this operator, this is any apply. So this operator could be, I have an internal data type called the GB operator. And this is just any operator. It's a unary operator, it's an index unary operator, it's a binary op. In the future, it'll be an index binary op, it'll be any operator I like. Because inside GraphBLAS, I don't give this feature to the user. Inside GraphBLAS, I can do this. All my ops have the same struct. They're really the same type. You just look into the content to say, what's the enumerator? Oh, you're a binary plus. You're an index op of some kind, or you're a unary op, whatever. But they all share the exact, so I can typecast like this between them. Now, macrofy assign is going to expect this to be a binary op. If this is not a valid binary op, I won't do that. Right? I'll have checked it before. This will fail. You can't typecast a unary op and just let's pretend it's binary op. It won't work. It's not a valid binary op. But apply, you could apply a binary op, bind second, bind first. You could apply a unary op. You could apply an index unary op. You could apply all 3. So just pass the op right there. So I call macrofy apply. Here's macrofy apply. Here's the op. Not binary op. Why is it not a binary op? Now that's curious. Where do I must have called. Oh, I know what. I know why. Okay. This path would not be taken if it's a binary op because I think I would have to treat that. I think I'd treat that as the apply in the EYs family. If you do apply with bind first or bind second, because there's 2 operands, so it's like an EYs. I think that's what I do. If I forget, I'd have to look at that. That's probably what I do. Okay, so yeah, I have a C, now it's a C type and the A type. And so now I'm gonna macrofy this. Now I pass in the bit encoding of this JIT kernel, which for this one is 4 zeros, triple E, 0E-FEC1, whatever the heck that is. Okay. So that are these, I guess it's like 38 bits. Hang on. This is an apply bind first. I'm in the wrong place. I'm in the wrong place. That's an EYs family that jitted this. So let's do macrofy EYs, which is 48 bits. That looks better. So I'm here. Yeah, see, apply bind first. So I'm doing a bind first here. So I'm going to generate this whole file. But the first thing I do, I have to, this is the S code. I have to unpack that to get all the bits. So I do bit masking and bit shifting to get all the bits, to get all the information out of that bits. So somewhere here, I guess it's 48 bits or 49 bits, I forget. And I did this in hexadecimal. I'm printing this in hexadecimal so I could actually walk through. And I've even have been careful to try to put boundaries. Like if I have a bit that's not used, let's see, like here, the formats of C, M, A, and B takes 2 hexadecimal digits, nicely packed into 2 hex digits. So that's C1. That's going to give me 8 bits. There's 4 matrices, so it's 2 bits each to tell me 1 of 4 formats for C, 1 of 4 formats for M, 1 of 4 formats for A, 1 of 4 formats for B. That's 8 bits total. That's the C1. Now,
And all the C1s then sort of apply to the same family of, in a sense.
well, for EYs, yes.
Yeah. Okay.
Now, I like in MXM, if I went to GB macrofy MXM, I probably do the same order because they're MXM and EYs are very similar. And so, yes, I share that. But there's more bits here. This goes to 63 bits. I try to use the same, like if I looked at these 2 files, yes, I try to use the same. Let's go to source Jitterfire GB macrofy EYs. So yes, these layouts I try here. I was able to share, make them the same, and the same thing was true here. I made them the same. I made them this the same and this the same. I made it all the way to here and even to here. Look, the multiplicative operator is just a binary op. Oh, looky, I need a binary op. So I made that the same. Okay, so that's 5 hex digits. Which binary operator are you talking about? And what's its input output types? This turned out to be the same. Yeah, is A ISO or not? Do you have to reverse the multiplicative operator? Do you have to reverse the operator? And then the rest is different. This is the EYs, and this is in the semirang, I need also the monoid. In the EYs, copy to C, I forget what that is doing. Cast copy. This is the to do. Let's see. I guess if I'm writing directly to C or not, I forget what that bit is for. Anyway, because the EYs is almost like MXM, it's just there's no monoid. Everything else is, and there's no summering, but all the types there's 4 matrices. Everything else is shared. So I try to line my bits up. I wouldn't have to, but I try just to be little bit, try to be consistent. This is MXM. I want to look back at the actual kernel and look back at just the macrofy EYs. So now I need to describe the operator. Let's see. I think the init preface grb init. The macrofy press. I think preface has actually written this header file include gbjit kernel.h. So these are the things I need to have for all the includes I need for my kernel. So now I want to just a print comment as to what is this guy? What is this? This is not an ISO kernel. C ISO is false. If I come down here, look for C is ISO, it's false. So C is not ISO. It's a full matrix, non-ISO. And since it's C, if you have an operator, but the output is ISO, I don't compute the value inside the kernel. I compute it outside in just a single function call. So I don't JIT that. So since C is ISO, if it was the ISO case, that's not here, then the JIT kernel does not compute the values of the output matrix. It only computes the pattern because the values are going to be computed elsewhere. But the general case is with a built-in operator, this is not a built-in operator. Oh, it's a user-defined operator. Okay. Or I guess GB wait, I think has it must create an operator of its own. I forget which it's called. It's a zombie killer op or something like that. Anyway, so what is I have oh yeah, like GB wait needs to use build, and so it needs to create an operator for that. It needs to create an operator called second, but it could be second for a user-defined type, which doesn't exist. I just make it internally, and in that internal operator is going to have a name that starts with a number, so that's not a valid C name. So I don't get confused with that. So otherwise, the operator is just given by its name. So the name is addGauss. I may be calling this operator with its inputs reversed because I don't want to have a new operator, but I don't know if the operator is commutative. If it's flipped, the way I would do a flipped operator down here is this right here, the definition of bin op. If this is flipped, then I do that here in this macro. I can pass yx with this instead of, so GB bin op here, this list of 5 parameters, instead of xy, it'd be yx. So I flip it in the macro using the macro. So the code itself doesn't care. It just calls the bin op, passes in 2 things, and the macro says boop, like that. And then this is going to call this static device function. So I print out a comment. All this does here is print out a comment. It says, who are you? Oh, I'm the addGauss operator, and it has 3 types, X, Y, and Z, and they're all of type Gauss. Okay. So I have a function here that I pass in up to 6 types. This is EY, so there are potentially 6 types for EYs or for MXM, because EYs, you've got CA and B types, and you also got X, Y, and Z types. So that's 6 types. I have to macrofy potentially all 6 of them. The C type, the A type if I need it, the B type if I need it. I may not need it, because if, let's see, B code of 0 means, what is B code of 0? One of the 0 and 15, one of them means, like, there's like 13 built-in types, right? So if it's 2, it's like int 8 or something. 0 is special. I think 0 means void, GB void. It means there's not going to be. I'll probably have it up here. No, it's in the encoding up here. Yeah, here we go. A. If A is ISO valued, then the A type, no, not ISO valued. Sorry. If I know that the operator is agnostic to the type of the A matrix, like the operator second, it doesn't need to know the type of the A matrix. I can't, even if it's ISO valued, I'm never going to touch the values of the A matrix. So that's type 0. That's type. I don't care what the type is. I'm not going to read the type. And that's a void, which means if I tried to access it, it would be a compiler error. So I don't get that. So that doesn't happen. And that's useful because it can tell me that I don't actually have to read that value of the matrix. Now, this does lead to an interesting API question. Think about this scenario, and this impacts potentially impacts performance. You create a binary op, z equals f of x, y, and it's the op is just z equals y squared. Say, square the second input. Why do you want to do that? Whatever. Take the log of the second input. Okay. And x, meh, I don't care. I'm not going to use it. Well, could you tell me? If you're not going to use it, could you please tell me? Because if you could tell me and I could keep track of that information, then I would know I don't have to load it. Because otherwise, think about what a kernel has to do. I have to call, like add gauss. I have to call this function. I have to call the binary op. I have to call the function. I have to give you the value of the A matrix you're asking for because you might want to read it. You might want to use it. And here we do. This is an add gauss, so it's adding to integer. It's the Gaussian integer. It's an integer with real and complex parts. So yeah, you want to read, I mean, it's adding x and y, so it needs to add the real and the imaginary of x and y and then add them together. So I do need x and y. But what if it was just, you know, an operator that says, I have one here probably, take the imaginary part. Maybe that would be a unary operator actually, say that says extract out the imaginary part. Well, let's see. No, that wouldn't be a good example. Anyway, you could easily have an operator which is agnostic of one of its inputs. Well, if the compiler is smart, it might be able to detect that I load a value from the A matrix and then never use it. Because what do? I pass it to this function, and maybe this function just doesn't use it. So maybe the compiler is smart enough to say, I don't need to load that value from memory at all. I don't know. Can I trust that? It'd be nice to know. I don't have a mechanism for this yet. It'd be very nice to know. And this is becoming even more important with the index binary op, or the index unary op for that matter. Because what does it depend on? F is a function, Z output is a function of X, the thing from the matrix, the row index, the column index, and the func value, the theta, say we call it. Okay, that's 4 different things. And if I call a user-defined GRB index unary op, I have to get all 4 of those things for the operator, and you just use one of them. Like I spent all this work to give you all these 4 things. I found the row index. I had to do work to find the column index because that's not part, or you know what row, I mean, oh, and the theta, well, the theta is easy to pass in, but all these are the things I have to work to give you. And you don't use it. It'd be faster if you could tell me, hey, here's an operator, but I'll tell you, just trust me. Now you could imagine asking a compiler, but see, that's, how would you do that? How would you do dependency analysis to say, oh, here's a little bitty function, and it's got 2 inputs and 1 output, and X is unused. Now, this is not an example of that here, but what if I deleted this? Okay, Z is just equal to Y squared, say. The compiler could tell that, oh, X is, you pass a parameter, you don't use it. Why are you doing that? Well, I have no handle to the compiler to do that analysis for me. So it'd be nice in the future. Think about when you define an operator, you could do a set that says, oh, by the way, Tim, talking to GraphBLAS, by the way, GraphBLAS, I just defined this operator, and guess what? When you use it, don't worry about the X value or the whatever. You don't need it. It's not needed by this operator. And you better tell me right, because I'm just gonna Otherwise, like, you get you a null dereference or something like that. So I don't do that, but then this gives me the 6 types. Now these 6 types, so macrophi type defs, I only had spit it out, only actually spit out 1 type. Why? Because, well, it turns out all 6 are the same for this instance. So type defs, I grab these 6 inputs. There's 6 different types: A, C, B, X, Y, and Z. I temporarily stick them in a both their name and the definition in an array of 6 strings. Okay, and I go through the 6, and if I see something's there, I'm going to print out the type def. But the first thing I want to do to know is, if the string is there, have I already type def this? Now I could have protected this with a macro. I could have said, if something is already defined, don't define it. That would just pollute this file. Okay, and so I wrote this scenario here, so I didn't have to do that. So I know that, so those 6 types, only one of them gets printed out because it's just Gauss. And I'll print out the macrophi the string, which basically just prints the string. And it's going to print the so GB macrophi string. It's really a bad choice of names. It's the string for the name of a user defined. It's macrophying a user definition is what it's doing. So this macrophi string is a bad. Is not just any old string. It's generating this right here. Actually, it's generating both of these. Okay,
Yeah, maybe
so
macrophi user defn, since it's called user defn.
yeah, exactly. Yeah, that would be better. And I do this. That's doing the it's a string for the user defined operator. That's why it's that. So the actual type def, yeah, is here. So I do the type def here. That's this. But I also want the same thing inside a string for the query function. So yeah, it's defining not just the type def, which is up here. It's defining the type def as a string, which then is only used for the query down here. So that's what it's doing. It's macrophying a string of a user definition. That's what this is doing. It should be macrophi string user definition or something like that. That's what it is. So now I have, so let's go to macrophi UIs. So I've constructed the type defs, all 6 of them, or just 1. And now I need to tell the macro, okay, what are the types of X, Y, and Z? I need to spit out the I've got the definition of the operators. No, I don't have the definition of operators. I got a definition of the types, the type defs. And now I want to define what are the types of the different parameters of the functions, X, Y, and Z. And this is a very simple function. If the name is void, then I print out a void. So if it didn't depend upon X, that would be void. So if I do by accident dereference it, I get a compiler error. Otherwise, so now I know what the X, Y, and Z type are. So these are going to be used, these are my template parameters, if you will, right? This is the template, the T in a C++ code, you have angle bracket T, comma, whatever, the T thing. Well, this is X, Y, and Z for this macro, or for this kernel. Okay, now I have to macrify the operator. Okay, now, and that goes down to here. Now this gets a little bit dicey because different operators are going to be macrofied through different places. This is macrifying a binary operator. I have a place where I macrify a monoid, which does some things and also does macrify binop. So I have different places where I'm calling a macrify of a binop, or macrify of a unary op, or a macrify of the actual user-defined operator, just for user-defined. And or for that matter, well, it wouldn't have to be user-defined. It could just be where's a different apply? Here we go. That's addcast. It could have been this. That's bitwise exclusive NOR. Okay. So this here will produce these two lines right there. It's like, there's your function. Z is the exclusive NOR of X and Y. Or it will, let me just pull these both up. It'll do this whole thing down to here. Okay, now this, again, I could have multiple definitions. Like you could have a monoid that has an operator that's the same as the multiply operator. It could be like a plus sum ring. Well, that's not a problem because I don't have to put out the definition. But it could be a zonky sum ring, and the zonky operator could be some user-defined thing called zonky, and it would appear twice. So all I do then is guard it with this if def right here. Like, oh yeah, you've been defined. So it only get one of the definitions. And so if you have like an add Gauss summering, you would see this operator defined twice, but it's guarded with that macro. And I could have done the same thing here. I could have spit this out 6 times, but I was always doing that in one place. And I just wanted to keep the file short and concise and easy to read. So I didn't do that up there. But here I'm using a different approach to avoid multiple definitions. So how do I do that? Well, the macrify binop is going to do one of these two things. It's going to define a binary operator. It's going to either define it, there it is, a one-liner, built in, piece of cake, or it has to do this whole thing. You notice the second one here doesn't generate a string. Like if this query, these are all using built-in operators. So there's no need to query it to say, well, what bit XNOR are you? Well, I know what bit XNOR is, and that's mine. No one's going to redefine bit XNOR. If they have a user-defined operator that it does a bitwise XNOR, it'll have a name, it'll be user-defined, it'll be a totally different path. So it'll have a string. But these are built-ins. I know they're all built-ins, so I don't need to check their strings. I know they're okay. I mean, if I say this is some code operator 044F or something, wherever I get that code for the operator, where's the operator? The binop E code. It's, let's see, which is this? This is 3 bits. It's probably that. Actually, it's just 1 bit. I think I don't need those 2 bits. This is 0 is 1 hex bit, 1 hex digit for this. This operator is 5x digits, 1, 2, 3, 4, 5. So 16444 defines all of this. So I've got 8 bits. That's 1 hex digit itself, I guess, isn't it? No, 8. Hang on, 2 hex digits. Sorry. So it's code 16. The binop E code is 16 in hexadecimal for this operator, and that turns out to be bit XNOR. And let's see if that's correct. Probably, I'm sure it will be if I've read it correctly. Well, it doesn't much matter if I did, but that's what it's going to be. And then 444 is probably these next four, Z, X, and Y, and 4 is probably int16. Yeah, so they're all int16 inputs and out int16 outputs. You can see here the types of the three are all the same, X, Y, and Z. So that's the 16444 in the encoding. And in this thing, it's, where was it? It was this digit. It was this digit. It was 00. 0 is special. 0 means it's user defined. Triple E, EEE is user defined, user defined, user defined. That's all it says. Triple E means all its inputs, all the three types are user defined. Which user defined? Well, I don't know. It's just a code that says it's user defined. Which one it is? Well, it's Gauss. How do I know it's Gauss? Well, indirectly. It's in the name, but it's not in the name directly add Gauss. It happens that the name add Gauss has the word Gauss in it, but that's not the type. The add Gauss is the name of the function. But here's the thing, I didn't have to put the types in the name of the file itself, because if you have a user-defined operator with user-defined types, you can't typecast those user-defined types. So by giving me the name of the operator, that fixes the name of, that defines what the types of X, Y, and Z must be. I can look at the operator and say, oh, look, they're Gauss, Gauss, Gauss. They have to be. So the binop E code would just be 0 if it's user defined. The XYZ codes in this case would be Gauss, Gauss, would be user defined, user defined, user defined. What are they? Well, you're going to have to look at the operator itself to get its name, and then look at the operator, when it was constructed, look at the types there, and that's where I get it here. So I get it there. These types, if they're built in, these types will coincide with these codes, but I have to pass in it both ways basically, because in the user-defined case, I have to get the actual the names. This is the only place I get the names. This is the only place I get the types for the user-defined case. So a hash code of 0, by the way, means I don't need to hash that object because it's built in. This is not the hash code of the that's used in the every operator, every type has its own hash code. Every submarine, every monoid, every operator has its own hash code. The reason I do that, I don't actually need this hash at the moment because I'm hashing. The hash at the end is which JIT are you talking about? Which JIT kernel are you talking about? But that's a function of all these different things that go into building that JIT kernel, which is an operator, a matrix, a data type, blah, blah, blah. Okay, so to speed up that process, I compute partial hash functions all along the way. So when I'm actually constructing the final hash of this instance, I can just like exclusive OR them together and put hash upon hash, and then only do a very little bit of hash computations at the very end. I pre-compute hash functions all the way up, so that then I can just exclusive OR them together to get a very fast new hash function for the whole thing. So that's why every operator, every type has a hash code. But 0 means I don't need to do that. There will be a final hash that's not 0, but it's not impacted by this hash because you see the hashing already takes into effect the encoding. So if it's a 16444, which is a bit XNOR with int16s, okay, well then that 16444 is in the S code already. The hash is unique already for that. Well, unless there's a hash collision, I handle that anyway, so that's a different issue. Okay, so I've macrofied this, and so macrofy binop now it's a big beast because it's got to produce potentially this or bit XNOR. It's got to produce, whoops, yeah, it's got to produce that string right there. No, there's the string. I just hard code it. I just take the code, and it's case 22. Oh yeah, that's a 16 hexadecimal. Case 22 in decimal is 16 hex. So that 16 tells this kernel that you're a bit XNOR, and this 444 says the input output types are all in 16. So now I just need to spit out that string. And so that's what I do. I grab the string and then I think I'm gonna grab it and print it at the bottom somewhere. There's a lot of built-in operators. Yeah, I'm going to like print it right here. So this thing right here is constructed here. I say, well, and it's not flipped because there's X comma Y. This is a thing that tells me whether or not you need to have a, you notice here, like, let's see, there could be a K in there as well, IKJ, I guess, the K argument. All of my operators are already indexed, even for something like bit XNOR. I can already pass I and J to them, even before we have the index binary op. This is a binary op, I pass I and J. Why? Because some of my binary ops are already indexed, the built-in ones, first and second, and first I, second I, things like that. And so for a user defined, I don't really have to change anything. I just have to get the user defined index binary op just to read in that I and J. So that's already the work is already partly done for the index binary op, user defined index binary op. One thing I have to handle here is the flip. You see this? See the YX, XY? That's all I got to do different to handle the flip. If I want to call this binary operator with X and Y reversed, I just do it in the macro. I just change this to YX and that handles the flip for me. Now, if it's a monoid, I have to do a little bit more stuff to it. Like I have to also define a update method. So if I go to, say, I don't know, let's look at it. Let's look at an AXB method. Whoops. So this is going to have a summary in it. Let's just pick one, doesn't matter which. Okay. At some point, I'll have to construct, where's the monoid? Oh yeah, here's the monoid. I'm building a monoid, and I'm gonna give it, so the binary op is, for the monoid, it's a plus pair. So the monoid is add. And so it's not called bin op, it's called GB add. The name of the macro is passed in by the caller. So in this case, macrofy ewise is just calling it bin op. But the monoid, I call it GB add. The monoid is not positional, it only depends on X and Y. And I also define an update. If it's a monoid, I want to be able to just do Z plus equals Y for the add. So I handle that. And so if you have a kernel for which the update is different for the CUDA and CPU JIT journals, and I have to kernels, I do two different kinds of updates. And that's only again for built-in operators. Otherwise, so what this is doing, let's see, let me go back to these two kernels here. Okay. So it's either say add Gauss or it's z equals some expression. Okay. That's not yet, that's just determined here. That's the function itself, is f has been passed in. F is, so this is, I guess, hang on, this is just the built-in case. I guess the user-defined case is up here. I use something else entirely. Yeah, so here, it's a user-defined operator, so I can't do a lot of special tricks. I first have to macrofy its definition. So that's with the guard and everything. That's all the way down to here. I have to macrofy that. That's what this function does. And then I give it, again, the flip is handled the same way. I swap y and x, or x and y. And then I have to print out the call to the function. And since it's a binary op, it's not an index binary op. There aren't no such thing as a user-defined index binary op. It's just the address of the 3 parameters. So that produces this. So all user-defined binary operators are going to look like this: the name followed by the parameters. And then if I need a user-defined update, I just have to call the same thing, the add function, with just z and z repeated with y. So user-defines are kind of, well, they're not clumsy, but I can't do anything special with the strings. I just have to call the function. That's all I know how to do. I can handle the flip without having to, change these parameters. I handle that in the macro the header. So that's user defined. There's another case here. If the output matrix is ISO valued, these operators just become empty. They're just elated. There's just the add function is just new line. It does nothing intentionally, because I'm never going to compute the numerical value of the output matrix. If I know the output matrix is ISO valued, I will be computing it with one call to the function, say, through the function pointer. If it's a function, if it's a user-defined function, I use the function pointer there. I don't JIT that. And that reduces, it's fast enough, right? It's one function call. And it reduces the number of JIT kernels. It does mean on occasion, I do need the function pointer of a user-defined operator. But in, say, Julia or Python, if you don't want to give me a C function pointer, because that's hard, just give me the string. Well, I'll JIT the function itself for the sole purpose of just being able to call it once, for, say, something like this case.
Yeah, that's
Outside
by
of
far
that.
that's by far the predominant usage in Python, and I imagine Julia too is.
Oh yeah, it'd be
It's a
ridiculous.
string, yeah.
Yeah, it's just the string. You don't want to give me the function. So I JIT. So what's going to happen with that operator is when you do grb op new or whatever, gxb, if you pass in a null, I'll immediately JIT that, just the function, to get that function pointer that you didn't give me. And then I keep it inside the operator. So that's a JIT that's called by the op new method, grxb binary op new, say. I'll the JIT right then and there. Before you use the operator, I'll JIT the function handle. I'll compile the kernel for that function handle and then stick that function handle inside the operator. So now I have it. Yeah, that was an important, very important decision that I made, because I was thinking about, I did this specifically for Julia and for Python, and not, well, for MATLAB eventually. I don't exploit user-defined operators in my MATLAB interface yet. I don't have a handle for that. But I was thinking about, like, well, how would you get the function pointer?
Yeah, and I'm going to be able to cover that in Postgres as well.
Yeah, Postgres, ditto, right?
Yeah.
Just give me the string. That's hard enough. Give me a C string of a string with a C function inside. Okay, all right, that's not so crazy. But It might be tricky if you want to write that in Julia. Oh, okay. You have to compile it into C, I guess. Translate maybe? I don't know. Okay,
And
maybe that's
there
hard.
are there are a couple of Python libraries where you give it a Python function, it will compile it to a C function, and then you can get the pointer. But
Yeah.
it's hard to say how efficient that's going to be versus, and if it's an operator, it's usually going to be something really straightforward in C.
Right.
A couple expressions and an assignment,
Yeah,
and you're
typically. Right. And the performance of that JIT, it doesn't matter because it's going to be JITted once. Once you JIT it, I cache it, so you'll never have to touch it again if you don't, unless you change the operator. So you run a new Python session, you give me the same string. I'll say, oh, I compiled that last week. So I DL open, I have the function pointer like that. I just DL load it, right? DL open, whatever. Um, and so I don't have to recompile it. And because it hadn't, I look at it, oh, you haven't changed. You match. You're the right one. Good, let's go. You've got the add Gauss whatever thingy already there. We're good. Um, so it's and it doesn't, the performance of calling that library to just evaluate the function once through the function pointer, not using that string as you see here for this static inline function. The performance of that never is going to matter because I only use that when I need to use it once or at most log n times. I have kernels, I have places where I'll call the user function log n times. I use that, for example, if you've got a matrix that's ISO valued and you have a user defined function to reduce this, and it's inside a monoid, and you want to reduce the matrix to a scalar using this monoid. But it's ISO valued. And the monoid doesn't care about the position of this value because it's not positional. It can't be. It's like replacing x plus x plus x plus x with x to the n. How do you do that? Well, you call plus log n times. And that's what I do if it's a user-defined plus, if you will. I'll just say plus. Now I have n over 2 things, and the value of those, all those n over 2 things is x plus x. Just repeat. It's just repeated logarithmic, doubling. If n is even, just compute it. If it's odd, subtract 1, compute it, and then apply with 1 and so forth. It's very simple recursive algorithm that at most calls the function log n times. So who cares how slow it is? It's not going to matter. Okay, so that is the so I'm basically having to, yeah, EUIs. So I basically have to, all the top level Macrofy family methods, they first start out by getting the code, getting all the conditions out of the code, and then going through the work of building building this file, I'm sorry. And they share a lot of things because Macrofy type you'll see in lots of different Macrofy families. Macrofy binup, you're going to see that several places. Um, and then if I need to do any casting, which I guess is here, yeah, copy A to B, copy B to C. Yeah, copy to C. I need to create wait, I'm not doing anything. Copy A to B, A to C. Why am I not doing anything? Add Gauss. I guess use not so let's see. Oh, it's because it's an apply. That's why. It's an EY's method, but it's an EY's method. It's apply bind first. I call that EY's because it's a binary operator. It just fit the family. Okay. So copy to C is false. That means the kernels are never actually going to use these macros. So they're just dead macros. I guess I wouldn't had to have defined them, but I do anyway. Just make them do nothing. So what these do, like for this EY is add, there's some places where you have to copy from the A matrix to the C matrix directly with bypassing the function. And the same thing from B to C. So I use it there. And so these macros are going to do that. They're going to do the typecasting at the same time, because you have to typecast, Cij equals paren type of C, Aij, if you will. That's what's happening here. So this is what this macro is needing to do. And not all the methods will do this, and apply bind first will never do this. Apply bind first, the values that go into the output matrix always go through the operator. So these macros won't be used, but I do define them, just they're no ops. I don't recall why I even have to define them at all. The function down below probably will never use them, but they're just empty macros. Okay, now 4 different matrices to work with. The C matrix, the M matrix, which is special, and the A matrix, which, it's not here. Well, no, it's not here because this is a bind first. There is no A matrix. There's an alpha scalar, if you will. So that'll be, some scalar will be passed in, but not a matrix. So what is this? What is this doing? This is doing apply bind first, and it's C equals F of A basically. But alpha A is a scalar. The output matrix is the output matrix is full for whatever reason. Why would I do that? Why would I make it full? I must be doing an apply in place. Maybe it's an accumulator. Maybe it's C plus equals A. I'm not really sure why. Apply bind first. Why is C full and B sparse? I don't remember. But anyway, there's 4 matrices. C is an output matrix. There's only one output matrix for any of these. So macrify the output matrix, and I'm always so I have to provide all these different macros to know, well, I can query at compile time and feel what format it's in. It's full. It's a full matrix. Well, and then I have the macro, the accessor macros. It says, how do I get the P, H, I, and X content of this data structure? Well, P is easy. That's the position of the top of each row or column. Well, that's a product. That's not looking up an array. It's a product. What is the name of the kth column? It's K. It's not hypersparse. Give me a row index. Oh, that's a mod function. Is it in the bitmap? Well, yeah, because there's no bitmap. So it's true. And then I don't have a GBX. I use other accessor functions to do that. So how do I know how many values there are? Is it ISO or not? Is it ISO at the beginning? Is it ISO on output? What's the type? So the underscore type, there's 6 of these, X, Y, and Z up here, and then C, M, and B. Now M, there was no mask, so the type is void, but there is no mask. So I just have a flag that says there's no mask. But if you ask it, hey, if I ask for the matrix at that position? Well, if there's no mask, it's always true. So sometimes I have one code that handles mask or no mask, and I just say, well, give me the value of the mask at this position. If there's no mask, it'll just be true no matter where you look. And there's no mask, so it's just true. So some of these things, even when there's no mask, I typedef the type of the mask matrix values as void because it's not there. You can't dereference the value. If I try, that would be a compiler error. So that just helps me avoid the compiler. I won't use this definition, basically. So, and the B matrix is sparse for whatever reason. I'm not sure why it's sparse, but the output matrix is full. That is interesting. I'll have to look at the kernel to remind me why I did that. So here, accessing the sparse matrix is different. You know, if you want to know where does the kth vector start, you got to look it up in the P array for the B matrix. For this output matrix, it's full. It's just a multiply. Where's the row index? You have to look it up in an array. What's the row index of a full matrix? It's a mod function, mod computation. So that's what the macrophi output is going to do. It's going to produce this output matrix. Now the macrophi mask is special. That might be a matrix, but it's very different because it will have some of the same things like M type, but a lot of the ways of accessing the matrix are going to be different. Or they're because, for example, I always know if you query the mask, you want to get a Boolean at the end if you query the value. So I don't have to handle user-defined types unless the mask is structural. But then if the mask is structural, I know that already. Say there would be mask, but it's structural. So the JIT kernel does not encode the type of the mask matrix. It doesn't need it. So you're going to be user-defined data type for a mask matrix if it's structural. If the mask is valued, you cannot have a user-defined data type of a mask matrix. You can't use a matrix with a user-defined type as a mask matrix unless it's structural, a structural mask, because you can't typecast. You have to typecast a user-defined type to Boolean, and there is no such way of doing that. Now, it'd be handy, maybe, to be able to say, here's my user-defined type. And oh, by the way, it has a typecast function to cast this type to Boolean, because then I can use it as a mask. There's no such feature in GraphBLAS to support a valued mask matrix where the data type is user-defined.
Well, I know Ray's asked for that, so maybe that's something we can add.
He's asked for that. He wants a, yeah. I could see why it could be handy because it's a hole in the spec.
Yeah,
it's a hole in the spec,
but not a bug. Just something we would just need to add.
Yeah, it's not a bug. It's just by design. It's not a super nasty limitation because, you know, but it'd be nice to have a way of registering for a type. How do you give me a function? If you want to give me a function to tell me how to cast a user-defined type to Boolean, then we can use it as a mask, a valued mask. Yeah, that could be added. There's a lot of other things that could make user-defined types more first-class citizens. You could consider arbitrary typecasting, but that starts to get really gnarly because you could have up to like 12 or 13 typecast functions. I don't want to do that. That's painful. Like if you want to cast it, you just write yourself a user-defined function to convert your function, like don't, please. That's too much.
But casting to bool makes sense for
Casting to bool would be
valued masks. Yeah.
Right. That would be useful. That's a hole in the spec that could be, but it would break one thing. Right now, there's no way to specify any typecast of user-defined types to anything from anything. They can never typecast to anything. So that would make an exception to that rule if we did that. And then you might argue, well, let's do it for any typecast from one user to define type to another one. Wow, think of, oh my gosh, really? No, don't do that. You can have an arbitrary number of typecasting functions from a user defined type to 12. How many other are there? Like 12 different built-ins, and there's unlimited number of other types. So you have an unlimited number of functions inside this type to say, here's how you cast to zonky to wonky and zonky to blunky and zonky to blinky and zonky to gauss and zonky to flunk and zonky to zwonk. I mean, blah, 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 blah. Oh my gosh, my brain explodes. I don't want to do that. And I have to look, oh, do you have one? Tick, 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 tick. No, you don't have it. Oh, you can't do this. See, it's an exception that starts to get the camel in the nose of the tent, right? To typecast a user-defined type to bool. Just that, maybe, but no more, please. Yeah.
Well, that one
So
we have a use case, so
there's a use
yeah,
case.
yeah. We don't need
There's a
to
use case.
venture into use cases we
Yeah.
don't have.
Yeah. There'd be a use case for that. Yes, I agree. Okay. So then I have to build the macros for A and B, but that's a different function. So macrify output is only for the C matrix. And I guess it's kind of boring the way I use it. I always call it, the names are always the same, C and C. Okay. But it's always, different. Well, here, there's a cast from one type to the next, Z type and C type and Z type. And here's no cast, so the two types are the same. So macrify output, what is this doing? Construct a macro to store values into an output matrix. So I have a macro called put C, I guess. Yeah. So how do I create a set of macros for the output matrix? Well, first I have to macrify the sparsity of that matrix, sparse, hypersparse, full, and so forth. And this also gives me accessor functions to how to get to those components of that matrix. So let's see. Let me do this. Oh shoot, that's not there. Let's see, let's not do it this way then. Okay, well, okay, so the C matrix. I have to macrify its sparsity first. And that's going to be the 4 different cases. So that's going to print out all the way here. I can tell it compile time, like, is it high? I can query this macro at compile time to say C is hyper, C is sparse, C is bitmap, and so forth. And then I can also put in these as well. So, oh, it's full, so it's defined this way. How do I get the number of values in the matrix? Well, depends on the sparsity. That's very simple usually. Is it sparse, hypersparse, sparse, or bitmap? It's just, I have a parameter called nvals in the matrix. If, does The matrix is ISO valued, that integer, this integer multiplication could be overflow, could cause integer overflow. So I guard against that by calling a function to compute it. And if it overflows, I pass in, I return uint like int 64 max or something like that. And so that just tells me how many entries there are. Then I'd say if it's ISO valued or not on input or on output, and it can vary. It can be different. If it's an output matrix, it could start out ISO valued. So I have one value of C to read, but then I have multiple values to write if it's not ISO on output. And then if it's ISO valued, the macro for writing it to it on output, then I never write anything. This is an empty string. It says, how do you put to there? No, you're done. Otherwise, I have a macro that writes to that value in the matrix. It's called the put C macro, because the name of the macro is C. And then it's going to produce basically put C here. It's going to produce this. And in this case, there's no casting. There's no type casting. Now, this is the Gaussian type. No, this is int16 type. Sorry. The Gaussian, whoops, where is it? This is the Gaussian type. The Gaussian type, it's also an assignment because it's just a type def, right? It works. It's a trivially copyable type. There's a name of that kind of type. So that's what putC does. Okay, so so I have to tell me how to, let's see, how to generate the output matrix. How to apply the element-wise operator. So the binary operator has three values and then the indices. The EY's op, I pass in the position, CX of P. So this just becomes this. It's a very simple translation because there's no typecasting. If there's typecasting, I have to have a temporary, or I first apply the binary op and get an output of type Z, and then the put will do the typecasting for me. If the C type and the A type are different, then I would have to typecast. And if this applying an EY's operator then would apply the operator and then the put function, the put macro will also do the typecast. We'll do the typecasting then from the Z into the type of the C matrix, which is then different in this scenario. So layers upon layers, macros upon macros, basically. What is the bin op? Oh, the bin op is just add. So this EY's op is now several steps removed. What is the add? Oh, it's defined up here. So this bin op is one step removed. This EY's op is like 2 steps removed from the actual operator. So macrofy the mask, that does a very simple few things. Maybe I won't go into belaboring that. But then I macrofy the input matrix, where it's going to produce all these things. And macrofy input and macrofy output are very similar. Macrofy output does the sparsity, ISO case, and the put macro for that matrix. Macrofy input is going to macrofy, it's going to print out the ISO case. It's going to, again, also macrofy the type of the matrix. I did that for the output type as well. The macrofy input, I have to declare multiple things here. I have to declare, where is it? So this is very similar to the output all the way to here and B ISO. So these things and these things, this is generated by Macrofy output. This is generated by Macrofy input, but this doesn't appear. There's no corresponding thing over here. It's just B is ISO or not. There's no two different ISO conditions for the B matrix. The C type, there's one type, and the put macro handles the typecast. With the input matrices, I have two different types because I have to, one is before casting and one is after typecasting. Here they're the same. And if I have to do the flip, the B matrix, the B2 type is basically either X type or Y type, depending on if it's flipped or not. And so I just couldn't keep track of that. So I made two types, B type and B2 type. And so whenever you read the value from the B matrix, that scalar shall be of B2 type. And when you want to declare a scalar, which I guess I don't need to do up here for the C matrix, that's how I do it. You know, it's of type Gauss. So there's a scalar of the type of the B matrix, but it's the type of the B matrix, I think, after it's been casted to its final usage. Okay. And that's it for the header. Now this is a special case of where I'm outputting not to a matrix. I can wait, this is an input. I can take input from a let's see. Oh, sorry. This is the more general case right here. But yeah, I have a get macro, get A, get B, and it's dependent upon the name of the matrix. And it handles all the type, any needed typecasting. So I have a cast input method. And I have a cast expression. Okay, how do you cast between types? Well, if the types are the same, it's just an assignment. So here I'm dealing basically, how do I have to generate the function, the strings to cast from one type to the next. But you might just say, well, just use the ANSI cast, right? What's the problem? Well, it's a little dicey because I could do that for bool, except for a complex type to bool is kind of weird. I don't like how C casts from complex to bool, or it doesn't work properly on Windows or something. I forget which. It's nasty. Complex is nasty because like you just can't cast, I think, from a Windows complex type to bool. It doesn't let you because it hates you. Windows hates you. So I just do it myself. I get the real part, I get the imaginary part, and I check if they're down 0. And that's the cast. Okay. The other gotcha is not a Windows thing. It's not a Linux thing. It's an ANSI C thing. Okay. Here's the problem. If you cast to an integer type from floating point, like 3.5, that casts to 3, I guess. It's like a floor or ceiling or something. I forget what it does. No problem. If you cast, though, from a float that's outside the range of that integer, the ANSI C spec, the GraphBLAS says just do what ANSI C does. ANSI C says that's undefined. And I don't like that. It breaks several things. It makes my testing super hard because then I get weird typecasting. And now it's random depending on what machine I'm running on, what compiler I'm using. MATLAB doesn't do that. They define it. So if you cast a floating point inf to int32, you get int32 max. That's a pretty decent answer. If you do that at ANSI C, you get 42 or something ridiculous. You get some ridiculous number. I don't like that. I want the MATLAB typecast. So I have to do it myself. So I have functions that do that. These are functions only used inside the JIT, so they're called JG. I have to define these functions, and I stick it in right here. I actually put in the function as a static inline. Here's some of them. Like this is going to be. Here's a good example. Okay. JG cast. I had to have lots of them. So this is a build. Okay. It's called a GRB build. It's called a GRB matrix build, probably, or vector build, one or the other. They're the same thing. The dupe is of type UN16. The T, let's see, is the T the input or the output? I forget. But you can build into a matrix of one type from an C array of a different type. Well, the types are different. Probably the output type is the T, and the input type is double. Yeah, that would make sense. Because then that means that, and I might have those backwards. I forget which is which. S and T. One is in, one is out. Okay. That means I'm going to typecast from double to an unsigned int16 type, uint16. So this is the function to do that safely. If the double value is a nan, like how do you typecast a nan double to a uint16? It's just not any number. Well, the best integer not a number is 0, because for a long time in history, right, 0 wasn't the number. It was a thing. It was a concept. One, how many sheep do you have? 1, 2, 3. You have 0 sheep. Why do you even say that? So the idea of 0 being a number is a new thing in the past, 500,000 years, whatever, 1,000 years. That's a new thing. So that's the best nan I can think of for an integer nan is 0.
Sure.
And if it's
Yeah.
and if it's negative, what do you do? Oh, it's just 0. You're casting a float that could be negative to the range of a uint16. So -3. The best I can do is 0. If it's overflow, you get uint16. Only then is it safe to trust ANSI C to do the cast for me. I've got to handle these cases. So that's what this is going to do. Now, here's an example for where when I macrofy a definition, I also need to put the guard. This macrofy definition creates a guard. It prints out the string as a C code, but then it puts a guard around it that says it's already done. Because why? Because, well, I might do it again, and in fact I do. It's appeared twice. If I was clever, this wouldn't appear in the code, right? I wouldn't need to do this, but it's easier just to stick it in the file. And if it's there twice, it's guarded. So only the first one gets used. So here's what I have to do. I guess S is the input. Yeah, so S is of type double. Yeah, so I'm reading in a set of triplets. The input triplet values are of type double. So I first have to load it. How to do the dupe? How to do the copy? Well, I have to cast. How do I handle the dupe operator? Well, I have to load in the value from the S matrix, cast it to uint16, load in the current value from the X matrix, compute the dupe operator, which is, where is it defined? Up above. This is second. The dupe operator is second. And then, so this is just Z equals Y. If I was clever, I wouldn't load in the X value. And then that's the value of TX. So I got to do my own casting if I have to cast from double to int. So I have to handle those cases, and there's a bunch of them. Right? Otherwise, there is no cast expression. I don't need to provide the cast expression. And let's see, if there's no casting, if the output is bool, if the cast is from input is type of float, the output type is integer, or all other cases just use the ANSI C11 typecast rules. So there I would actually produce, you know, the standard typecast expression. So this is a lot. And I think that's it. Yeah. Oh, and then at the end of the day, I put in this. So if I go to back to that function, here. So these are pound includes that all EY's methods use, and these are typically cleanups. So like, oh, if you haven't defined a certain macro, here's the default macro. Because that are defined up above. That's what these things do. They're catch-all. For if I chose not to even define something, I get the defaults, and the defaults are saying if it's not defined, here's the default macro. That's what this does. Okay, so finally, I think I'm back now. That's the JITify family. Okay, where's the JIT family here? Build a family. Macrofy family. Okay. Finally, I printed this last pound include. Now I need to handle this case. Okay, these 4 lines of code allow this C file, which I just wrote, to be used in 2 different ways, as a runtime JIT or as a pre-JIT. And this, by the way, everything you've seen so far, it's identical for CUDA versus OpenMP, right? There's no difference here except for maybe the type of the file and the preface. Otherwise, that's it. I mean, this family here, it doesn't even know where, well, actually, it does look, hang on, is there, in the Macrofy family, I don't think there's anything there that's CUDA specific, except some of the built-in operators are slightly different in CUDA for they're slightly, I have faster variants. So I have an if-def CUDA kernel in the definitions. Okay, but this thing is not even in the CUDA. This is JIT versus pre-JIT for both C file JITs and CUDA JITs. Okay. If you're a runtime JIT, I pass in the flag when I compile it, GB-JIT runtime. I tell the kernel, you're a runtime JIT. You're a JIT being compiled by the JITifier at runtime. If you're not, then you're a pre-JIT. You have been copied. I've copied that C or CUDA file into the GraphBLAS source directory itself, in a folder called pre-JIT. And then CMake will look at those and build a list of them and compile them all. And they're baked into libgraphblas.so. Well, when I do that, I can't just call them all GB-JIT kernels. I have to call them by their full specific name. which is these two, one for the kernel itself and one for the query function. And then what CMake also does is since I'm compiling all these kernels, now they have unique names. I need to make a table, and the CMake does this. It makes a table of three things: table of names, like this would be GB apply bind first, and then the code, add Gauss, and add Gauss, and then a list of two arrays with two function pointers in it, the kernel and the query method. There's three different arrays of size, how you have 100 pre-JIT kernels, each row size 100, and then I have a function that is able to then give those three tables, three arrays, to the caller, which is the JITifier here, that says, I'm GRB init, I'm initializing the JIT. I need to pre-hash all the pre-JIT kernels. They get stuck into the hash table at init time, and they're not loaded, they're not compiled. They're already in libgraphblas.so, but I need the function handles. I can't deal open or deal close them or deal send them. But I do need the function handles, and that's what I do at init time. And they all have to have their own name. What's the best name to use? Well, the name of the kernel. Right? This is unique. There's only one file with that name. If there's two, that means that are different. That means they have potentially different, type defs for the user-defined operators. But see, that's invalid. I'll delete one. I will only have one valid one with that name. So that's what these lines do. They handle that. They enable this file to be copied directly and plunked it back into GraphBLAS, rebuild GraphBLAS. Suddenly you've got pre-JIT kernels, and the files don't have to change. Because this is not defined when I'm compiling inside for GraphBLAS itself at compile time for GraphBLAS. Okay, finally, we get to the algorithm. And let's just for grins, let's look at the algorithm. And that's also produced here. Actually, this printf is doing two things. It's printing the JIT runtime versus pre-JIT, and it's also including the actual source code of the kernel itself. It's one line, and it doesn't even get its own printf. It's like this is a fine little piece. Let's just look at that just for fun. Let's look at what is it? It's apply template GB JIT kernel. No, sorry, it's JIT kernels GB template GB JIT kernel apply bind first. There it is. Oh, that's boring. That's it. That's the file. Okay, so there's a prototype for it, and which I don't want to write twice, so I use a macro because I use it in other places as well. But then it's just the function just includes my template, and this template is also used for factory kernels. It's also used for the generic case, and so now that's the actual algorithm finally. So that's going to be in the apply template, GB apply bind first. There's the algorithm. About as simple an algorithm as you can imagine. It's so simple that when I call the kernel, I don't even pass in the entire input-output matrices. Okay, this is a bind first, so it's passing in a scalar. So I actually pass in raw pointers. I'm calling the kernel. I don't pass in the GRB matrix C or GRB matrix B and then extract out its pointers to its pieces. No, I just actually pass in the numerical arrays. It's just to apply one-to-one, right? All the input values, all the output values. And I guess this doesn't handle the ISO case, but maybe I do it here. If B is ISO, this is going to be called. I'll do it separately. I won't call this kernel anyway. But this is it. I mean, just literally iterate across the entries and do them. And there's no row index, there's no column index, because this isn't a apply of a indexed binary op, which there is none anyway. It's just an element-wise operator for the input scalar X and for the entry from the matrix B, which is just loaded from the array, and apply the operator. So that's it. I mean, the algorithm is trivially simple, but everything in this algorithm goes through these macros. All these macros here. What's the C type? Oh, well, this C type is Gauss. Do I need to check the bitmap of B? This handles the case where, well, what if B is bitmap? Then C will be bitmap on output with the same bitmap as B, so I don't have to copy that over. But I want to not apply the operator if the bitmap says it's not there, because I want to read garbage and apply a function I don't know to garbage, so I skip it. Well, but B is sparse. So how do I say, well, give me the bit which this is true? So this becomes if not one, continue. Well, if not one is always false. So the compiler just says, ignore this. This is an example of where actually all four data types, all formats, sparse, hypersparse, bitmap, full, all coalesce down to a single algorithm. And that one line enables this algorithm to handle the bitmap case for B and C as well. Otherwise, I declare the value of B. So says B is Gauss. I read it. So I do Bij equals Bx of P here. And then I apply it to the operator that says the bin op, which just says, oh, I'm going to call add Gauss, say, for this case. Or unless it's bx bitx nor. So there's another bind. Oh, this is bind second. I guess this is going to call a bind second kernel. Oh, okay, that's slightly different. Apply, whoops. Apply template GB, apply, but it's going to be very similar. Bind second, there it is. There's a bind second. I have an A matrix instead. And I get a value from A, I declare it, I get it. This will also do the typecasting and pass it to the operator, which is just simply a bitwise exclusive NOR. Bind second. So I don't know why you'd ever want to do this, but it's one of my tests. It's doing a bitwise exclusive NOR with a scalar and a matrix as an apply method called the GRB apply. And it's just a trivial algorithm. But the wrapper, getting to that instance is not trivial. Compile that code. There's no function. It starts with curly bracket, right? That's because the JIT kernels, PB JIT kernel, JIT kernels, template, GB JIT kernel, apply, find first, say the function parameters are right there. And I do that because these templates are sometimes used in different contexts with different parameters, different functions. So
yeah, makes sense.
A lot of my templates have no function headers. They're just pieces of code.
Just bodies. Yeah.
Just some chunk of code that I'll slap in. Sometimes the templates include the function headers, but many times they don't. Most of the time they don't.
Well, just to give a little time check here, I've got a hard stop at 30 minutes.
Yeah, we should wrap it up soon. Actually,
we're dipping into algorithms a little bit, which is the next session. Anyway.
We are exactly. But we're not okay. This was the macrophi EWISE, but let me go back to G by Jitifier. So macrophi family. So I just wrote and then I have a function which produces this, and let's not go into the detail of that. Okay, it'd be nice to reach a stopping point. let's try to go to another few minutes here and not talk about algorithms anymore, but say I've written a file, done F closed. I've got the source file written. Now I have to compile it. How do I compile it? Well, if it's a CUDA kernel, I call NVCC. If the JIT is supposed to use CMake, I call CMake. I create a CMake script to compile this one little library that has this one little kernel in it. Otherwise, I call the compiler directly. So this is what's going to call the compiler. 3 different ways to reach the compiler. NVCC, CMake, or like GCC, for instance. So what do those things look like? Let's look at the compile methods. CMake literally just writes out a temporary file. Let's see, it removes, it uses CMake to delete the build directory if it already existed. It creates the build directory. Then it writes a CMake file inside the build directory with a project called gbjit, because who cares what the project name is? And it's a runtime method, and sets the flag, adds the new libraries, link libraries. It's building a CMake to build compile one CMake for one JIT kernel. At 22,000 JIT kernels, so there's 22,000 CMakes that get built inside the build folder. This is going to get deleted once the build is done. Then I do the CMake configure, I do the CMake build, I shell out. This is the JITifier command function. It's just a call to system. Run a command in a child process, and that's it. It just calls system. So, and how do I do that? When do I do this? When I need to talk to the compiler. So I first call CMake to delete a folder, and then I build this file, the CMake file, and I configure with CMake, and I tell it what compiler to use, because I don't know what it is. It could be anything. It's defined at compile time of GraphBLAS, or changed later. And then I build it, and then I install it. But the installation location is in the cache, the library archive runtime destination. It's in the lib folder. That's where the .s goes, .so goes. That's where I install. So I build, compile, install, and then I obliterate the build folder because I no longer need it anymore, including the whole CMake script was actually built inside the build folder, which is usually not typically done, but this is a temporary CMake script. NVCC is different. It's not a lot of it's a directly shells out to the NVCC command. And then it puts in all the whole command directly for compiling and linking as a single call to the system. So this is more typical of, let's look at this. This is the direct compile of a C kernel. Okay. And this is the CUDA is experimental or in production, or not in production, in development. This is typical default case this is the default case for a JIT kernel. I'm going to shell out, I'm going to sprintf, a huge long sprintf, and then call system. And then I'm going to remove the object file. So 1 call to system as opposed to 5 for CMake. But so what does 1 call to system look like? Well, I make sure it's this SH compiler, which this was a Windows thing, I think. When you call system, you may not get the right. This works on, this is all using the SH shell. And you can do this on Windows. No, on some Windows. How does this work? I think on Windows I wasn't able. I think with Ming G, W or something, I could get this to work. I think for Windows, I have to use CMake to compile everything. CMake is slower. This is faster. So I have all my include files. I have all my includes for directories. The output file is defined. This is all cache. And then all these %S's are all going to be down here, all these together. And then I actually have two commands glued together because why call system twice? I build a one string with the compile and link as a single string. Shell out to that. So there's another command to do the link with the right flags and everything. This is crazy code. So that's my JIT. I just shell out to the compiler. I have to give it a command. How do I do that? Well, I know where I'm compiling. I know, what the include files are. I know where OpenMP should be linked against. I know, you can tell me any additional C flags. Like if you need a -I, you can augment the C flags. You can read the existing C flags and you can stick in -I something. Like -I, you got to look here to find, because maybe you gave me a preface with pound include something. Well, then you need to write -I for that. You need to tell me that with GRB set, and that'll change, say, the JIT C flags, I think. I don't have a way, no, I don't have a way of just specifying new include files. You have to just augment the C flag settings. Yeah. So this can be customized, in other words. You can change the compiler if you like. See, by default, let's just look at the one compiler. By default, okay, initially there is no C compiler, okay? But when GRB init comes along, I allocate this space and it defaults to the macro gbc compiler, which comes from gbconfig. Which is this mouthful, because I happen to use SPAC GCC 12.2 from SPAC to compile GraphBLAS. So to compile the JIT kernels, it's going to use the same thing. Until you come along and say, whoops, my internet connection is unstable. Can you hear me?
Yeah, I can hear you.
Okay.
Yeah, I didn't see any problem.
Okay. Unless you call GRB set to change the compiler. And so I'll free that string and copy it in again. So if you want this C compiler to be something other than the C compiler that was used to compile GraphBLAS, you can tell me that with a GRB set. Then all subsequent calls to the compiler will use that compiler you've told me to use. That's possible with this set function here, which is called, and then I just use it here. I just shell out to what? To the C compiler. So it's building a pretty big, long string for this case, but it works. And I'd use the same function, the same string, the same C compiler to do the linking as well. And I trust that the compiler will understand. I'm trusting that the compiler will understand the standards of -I, -O, -C. That works on Linux, Mac. Sorry, I don't do this on Windows. With Windows, the default is to, you got to get all the stars aligned. You have to use, like Windows, you can use the GCC compiler, for example, with the Ming build system, right? You can, the Ming package. But by default on Windows, I use CMake. Actually, CMake doesn't work in Ming. I have to use this feature. In Ming, I have to, if you're compiling with this build system in Windows, I can't use CMake. It doesn't work. I haven't figured out why. If you're using MS Visual Studio, you always have to use CMake, but it just works. You can't tell me to use it. You can tell me in a GRB set to use direct compile or to use CMake. Well, that works on Linux. You can select between the two, or Mac, you can select between the two. In Windows, you're stuck. And you can't change it. Yeah, one or the other doesn't work. I prefer just to shell out and run the command, but Windows doesn't do by default, Windows can't do this. If I was clever, maybe I could specialize this to shell out to, instead of -I, it'd be like it'd be like a /, whatever the Windows, gobbledygook is, to set flags and such. Maybe I could, but I haven't figured that out yet. So I just use CMake. CMake's a lot simpler and portable, more portable. So that's it. That's the entire JIT. There's more. There's that hashing, hash lookup. I didn't dive into that. What else do I have in here? There's the hash table. There's a sanitization when you set cache paths. I don't want the cache path to have like rm-rf star in it, slash in it or something, because I shell out and I put in the cache path. That could be a command, and I'll execute that command. So I have a sanitization of some of the strings. I haven't talked about how I do the init, how I spit out how I do all the pre-JITs. I have to build them all, stick them in the hash table, extract the source code. I haven't talked about that. How is extracting the source code here for each file. I use a Z standard decompression. How the JIT, this thing called the JIT package, where I bundle up all my source code inside the lib-graphblas.so as compressed binary. And then GRB init comes along, reads those, and belches them out into the cache folder. What else? I mean, this is just a lot of helper functions, setting the compiler, setting the C flags, a lot of very simple things. A lot of OMP critical sections here in this function, because lots of my own threads. No, sorry, lots of user threads within the same process could be calling GraphBLAS simultaneously. So they're all protected with critical sections. The query, then we delved into the load, and that was the meat of that was the hefty part of this. The JIT load and compile process. We walk through all of this. But the lookup, like the hash table handling, I haven't described how that happens. Hash table insert. Free and entry in hash table. I showed this. Oh, then the compilation. I showed you this. What else? Oh, and then finally, the JIT hash. Here's the JIT hash. This is just a wrapper around this hashes the entire encoding struct, and this hashes some blob of bytes, except maybe it's not jittable. If the thing's not jittable, the answer is infinity. That's the hash function. If there's nothing to hash, I get 0. And then I call the XX hash on the rest of it. Now, if by chance the XX hash method returns one of my two special cases, so 0 is a special case. 0 says I don't need to find a hash function for this. It's like a built-in operator. Or uint64 says, well, it's user defined, but I can't hash it. These two are special cases. I don't want the hash function when it's not a special case. This is the general case. This hash function is the general case. It's not one of these two cases. So this had better not return 0 or infinite uint64 max. So if it does, I just return an arbitrary number. So I preserve those hash output functions of the hash 0 and uint64 to mean it's either not need the hash or it's not hashable. Now, this will hardly ever happen, right? I call some random hash function, I get some random number. What's the chance it'll come up 0? Pretty low, but I want to avoid that. 0 is special, uint64 is special. So that's why that ternary is there, just double check. I basically, if I get back 0 or uint64 from this hash function, I don't do that. I use magic instead, which is a magic number I use to detect. It's an arbitrary 64-bit number. And I use it to detect whether or not a matrix has been initialized or not, or freed or something like that. It's just and it's not 0 and it's not uint64. So that's the JIT. That's the bulk of it. The things I didn't, there's a lot of the JIT here I didn't go through. I mean, I didn't go through every single of these functions. But I went through many of them. Like unify CUDA atomic, you did see that. But I knew
Yeah, and with
about
the high
all.
level structure, someone can just drill down. Once you know the
Yeah,
high level structure, you just
exactly. Exactly. Yeah, yeah. And it's all inside this JITify folder as well. Everything you need to know about the JIT is right here or here. There's the JITifier itself, but then there's the 44 JIT CPU JIT kernels. And there's the 44 wrappers for those JIT kernels. They always end with underscore JIT. And these things are the things that do they all look the same. They call the encodify, they call the GB JIT load. And then if they find the function pointer, they call the kernel. And I have this similar kind of construct over in the CUDA folder, but I just don't have it broken up. I have 8 underscore, these are JIT wrappers. Okay. And then I don't have any kernels here, but I have them in here, template. They're all here. They need to be broken. I need to reorganize the CUDA folder. But these are the 8 variants, or there are 9. If you go to JIT kernels, you'll see some header files, and then the templates. There's 44 of them of CPU JIT kernels. And then over here are the 8 CUDA JIT kernels. And then these things really belong like in an include subfolder, but they're just stuck. Anyway, the CUDA source codes need to be kind of rearranged to match the source folder for the CPU side. And some of these files need to be renamed a little bit, but we're getting there. Yeah, so I think that's the whole JIT.
Awesome. Yeah.
There's a lot of stuff there. There's a lot of algorithms under the hood. You saw one of them, which is a trivial one. Some of these algorithms are 10,000 lines long. Um, this folder here is everything. It's all my source code that I need. It's spit out by libgraphblas from libgraphblas.so by JRB init. I extract my JIT package and plunk the source code here. You know, it's what is it? 27, close to 27,000 lines of code with 11,000 lines of comments or blank lines, 244 files. GraphBLAS.h is there. I've got all my include files for everything, all dumped in one place. These are both, there's CUDA stuff in here. Actually, are there CUDA? No. Yeah, there's CUDA stuff in here. There's any H files go here, and then template is a massive thing. This is the template folder. It's everything. It's all dumped together. It's not split by, oh, here's add, here's matrix multiply, here's apply, here's all the CUDA stuff. It's just all dumped in there because nobody needs to read this. Just the files are unique, so that works. All the kernels, all the CUDA kernels, all the templates, all the methods. It's all there, and it's big. You know, 14,000 lines of algorithms basically,
Right.
and kernels, kernels. So it's like 1/8 of all of GraphBLAS goes in this particular, gets copied into this particular folder. GraphBLAS itself is like 120,000 lines of code. So the JIT kernels aren't like the bulk of the work. There's a lot of work that goes inside GraphBLAS. It's not JITted. It doesn't need to be JITted. So
Cool. Well, I gotta roll. I gotta
yes, I got to run
another thing
too.
to go on.
And
Yeah.
yeah, so next time,